Our next lesson is are going to be on equilibrium expressions that involve pressures. So remember, in the gas phase, we can express or write the law of mass action in terms of pressures. So what I've given you here, you might want to pause the video to copy this down and then start the video again. I wrote the K expression in terms of pressures only because all of these are pressures. So we would say Kp is equal to the partial pressure of ammonia, because that's our product, raised to the second power, divided by the partial pressure of the nitrogen, raised to the first power, because that's the coefficient of 1, times the partial pressure of hydrogen, raised to the third power. At a given temperature, there can be different equilibrium expressions or different equilibrium positions, but only one value for K. So it is temperature dependent. So K is your equilibrium constant at that particular temperature. So at that given temperature, that would be the equilibrium constant once you solve. Now there is a formula that relates our Kc to Kp for a given reaction. Now this is a formula that if you know your Kc or your K where concentrations were involved, you can plug in and solve for Kp. Now likewise, if you knew your Kp and were asked to find Kc, you could plug in the Kp and then rearrange and solve for Kc. So we can use this formula if we know one K value in pressures or concentrations and find the other. So let's take a look at how we would use that reaction and that formula. Now the R we use here is the regular ideal gas law R, 0.08206 liter atmosphere per Kelvin mole. The temperature does have to be in Kelvin, again, to get your units to cancel here. And delta N, this value here that's raised, is equal to the sum of the gaseous coefficients minus the sum of the coefficients of the gaseous reactants. So if you go back to that original equation we looked at where the coefficients were J, K, L, and M, you only use gases, that's very important, and you take L plus M and J plus K, and then you subtract. So let's practice for this particular reaction that we have. So we have the given reaction at equilibrium, and it wants to know what is Kp if Kc is equal to this. All right, so let's write down the formula. Kp is what we're solving for, equals Kc times RT, that's R times T, to the delta N power. Now I'm going to go ahead and find delta N. I like to do that over to the side first. So we're going to look across here, gas, gas, gas. All these are gases, so take your coefficients of the gaseous products, which is 2. And then from that, we're going to subtract the sum of the gaseous reactants, 2 plus 1, which is 3. So 2 minus 3 gives you -1 for your delta N. So now we're going to plug in. Kc was given 4.6 times 10 to the 4th liters per mole. And then you're going to take your R times your T, so 0.08206, and that's liter atmospheres per Kelvin mole, times the temperature, and the temperature has to be in Kelvin, and notice it's given in Celsius, so 25 plus 273 is going to be 298 Kelvin, and then that, once it's multiplied, is raised to the -1 power. So I'm going to go ahead and multiply 298 times 0.08206. And notice with your units, the Kelvin here cancels with the Kelvin, okay? And this is raised to the -1 power. So let me just point out to you that that will be the same as saying 4.6 times 10 to the 4th liter per mole. If this multiplied by this value to the -1, it's really being divided by it. Okay, so I went ahead and got this answer, the 0.08206 times 298, and that was 24.5. Now, if you look at what happened here, this left us with liter atmospheres over moles. So I'm going to put this here, liter atmosphere over mole. Now look at your units. The liter per mole cancels with the liters per mole here. And so our final unit is going to be like 1 over atmospheres, which is just atmospheres, which it should be because we're talking about pressures. And so you got 4.6 times 10 to the 4th divided by that 24.5. And that's going to give me, I'm going to round this to 2 sig figs, 1900 atmospheres. All right, I did not clear my calculator, by the way. Okay. Let's talk about heterogeneous equilibria for a minute. The position of a heterogeneous equilibrium does not depend on the amounts of pure solids or liquids present. So if you look at the equilibrium expression for this reaction here, where you have a solid, liquid, and a gas, remember we do not use solids or liquids in our law of mass action, only gases. So if you're going to write your equilibrium expression for that, you would write for Kc, concentration of Cl2 to the first power. If you were going to write it in terms of pressure, since that's the only state of matter it's in, you could write it in terms of pressures. You would say Kp equals partial pressure of Cl2 to the first power, because again, that's just to the first power. You would not include pure solids or liquids if you have heterogeneous equilibria. Consider the reaction below in which you have N2O4 placed in a flask and allowed to reach equilibrium at a temperature where Kp is 1.333 atmospheres. At equilibrium, the pressure of N2O4 was found to be 2.71 atmospheres. Calculate the equilibrium pressure of NO2. So remember, your law of mass action will be Kp is equal to partial pressure of NO2 squared divided by partial pressure of N2O4 to the first power. Now they told us Kp, so plug that in here, 0.133 atmospheres. And they're wanting us to find the equilibrium pressure of NO2, which is this value. So I'm going to say partial pressure of NO2, that's our X, and that's squared because of our law of mass action. Now notice they told us the pressure of N2O4 was found to be 2.71 atmospheres. So we're going to plug that in here, 2.71 atmospheres. So we need to cross multiply here, 0.1333 times 2.71, and that's going to give you 0.361 atmospheres squared equals x squared. So we need to take the square root of both sides. And that's going to give us, for the partial pressure of NO2, our x value, 0.601 atmospheres. So that's how we can use our law of mass action to solve. That will end the lessons for this section of notes.